Okay, welcome to a new user space has entered this talk. We're going to discuss how we integrated RISC-V hardware features such as PMP that support into the Zephyr real-time operating system. Thank you for joining us at Embedded Linux Conference. Thank you for watching, listening, joining wherever you may be. First, let's do a couple quick introductions. We work for BayLibre, which is an embedded software consultancy based in the south of France. We have around 40 software engineers with a strong open source focus. So we are active in the Linux kernel community. We've often been in the top 20 kernel contributors. We have several maintainers. But we're also maintainers and collaborators in the Zephyr operating system as well. We also are quite active in U-boot, ARM-trusted firmware, Opti, several Yocto layers, automated testing, OTA updates, and so on. So Alex Mergnat is the primary author and engineer behind this work. He is based in Nice, France area, and his expertise here is in the RISC-V user space and PMP, which is the primary subject of this talk. He did all of the core engineering for this work. I am just presenting that work. My name is Kevin. I am a co-founder and senior engineer at BayLibre. I'm primarily a Linux kernel developer and maintainer. I do live in Seattle, but I have contributed a little bit to Zephyr. I have one patch in Zephyr. It happens to be a grammar fix, but it's still a patch in Zephyr, so I at least have some credibility in Zephyr. But actually, Alex is the primary engineer behind this work. So a brief agenda overview. So first I'm going to introduce a handful of Zephyr features and terminology that we will cover in the talk, and then give a little introduction to some RISC-V hardware features that are relevant to what we needed to implement, and then talk a bit how we did user mode threads and protected memory. And then a little bit on some challenges that we ran into and which led to some ideas for some future work. So with that, we can get into the work. So first, let's talk a little bit about Zephyr, introduce some of the features. So first of all, for the embedded Linux crowd, Zephyr is another operating system. It's a Linux Foundation project, but it's a real-time operating system focused on typically smaller types of cores that Linux would run on. In this case, we're talking about some small microcontroller class chips that Zephyr is targeted at for this work. One of the concepts of Zephyr that'll be familiar to Linux users is the notion of privilege mode. So Zephyr, just like Linux, has kernel mode and user mode. Except unlike Linux, Zephyr has user mode is actually optional. So you can run everything in kernel mode on the types of cores that don't have any privilege separation. So Zephyr, by default, the kernel will run in as the highest privilege level, is where the kernel mode is, and that's where the Zephyr OS kernel is running. As well as kernel threads can run in this level, so this is kind of the default configuration for Zephyr for types of chips that only have a single privilege mode. But what we're interested in for this talk is adding an unprivileged user mode support for RISC-V cores that actually have hardware support for that. So this is where we can add support for this Zephyr user mode threads, so that threads can be protected from each other with some hardware protection, such as a memory protection unit. So throughout this talk, you'll see this little Zephyr flag with some links. So if you want to look at the slides later, all these links will take you to Zephyr, the official Zephyr documentation, which will go into more details on each of these topics. So the Zephyr documentation actually is quite good on the internals, I'm giving a quick overview of these Zephyr features, but the documentation is quite good, so you can dig on your own here with these links. So another feature of Zephyr that we'll be getting into is just how Zephyr does stacks and stack separation. So there's two concepts here that are referred to a little differently in the docs. So the first is stack separation, where each thread has its own stack, and that stack also includes thread local storage. So all the memory and data that's specific to the thread is stored in the TLS section, which is kind of combined in Zephyr along with its thread stack. So combining these stack separation with hardware support, such as an MPU, we can support what Zephyr calls MPU-backed user space. So that's basically memory protection of user space threads against each other and from the kernel as well, so that threads can't tinker with the kernel. Another concept in Zephyr that's called stack protection, and that encompasses a couple things. So that's hardware stack overflow, and that's again where we can use the MPU to actually detect accesses outside of the normal stack region, and that's an optional feature in Zephyr. Like most of these things are optional at compile time. So if you don't want or use hardware stack protection, there's a software alternative as well using stack canaries that can be implemented as well using with some compiler support. So later on we'll talk more about the hardware backed features, because that's what we're interested in for this talk for RISC-V. So another concept in Zephyr that terminology-wise might not be similar to if you're familiar with Linux is the notion of memory domains. So by default, user mode thread in Zephyr only have access to the minimum set of regions. So obviously they need access to the executable text region, the read-only data, and as well as a stack, which includes the thread local storage. So that's kind of the bare minimum that a user space thread needs. However, if you want to do things like shared memory between threads, or have a memory region that's shared between the kernel and a user mode thread, Zephyr provides a memory domain API. And that can be used either at build time or at runtime to define regions that are shared then between threads and the kernel, or between threads, or between a thread and the kernel. And this can be MPU backed, so this can be just like the other region can be enforced by the MPU, so that accesses outside of memory domains that you have access to will fault or trap. But a little bit of foreshadowing for the talk. For MPU-backed regions, we need to be careful, because some MPUs, especially some of these smaller microcontrollers, even if they have MPU, there's a limited number of regions that can be protected. So we have to be aware of that as well when using the memory domain API. But we'll get into that in a little more detail as well. Okay, also potentially familiar to Linux users is kconfig. So Zephyr is configured at build time using kconfig, just like the Linux kernel. And here's a handful of options that are involved in the features that we're talking about here. So the one thing to note here is user space itself can be configured, enabled or disabled in Zephyr. So this is the case where if you don't have any privilege levels, you don't have any need for a separate user space. So that can be turned on and off, and all these features can be turned on and off at compile time, including the memory domains that I just talked about, power of 2 alignment for various regions, and MPU support. All these things are optional in Zephyr. Okay, so that's a quick overview of the Zephyr kind of terminology and landscape for the features that are relevant to what we're after for this talk. So now let's move on to RISC-V, some RISC-V hardware features that are involved with what we wanted to implement. So first of all, in RISC-V has hardware privilege modes. So in the RISC-V spec, there are a few privilege modes that are defined. The first of which is machine mode. And machine mode is the highest privilege level. And that's the only privilege level that's required in the RISC-V spec. So before we started our work, the Zephyr port to RISC-V supported this mode only, and that's where the kernel and threads all ran in machine mode, so at the highest privilege level. So there's no switching between privilege modes, and that supports RISC-V cores that only have, this machine mode. So this is the minimum mode, and that's kind of the basic RISC-V port to Zephyr. We'll use this even before we started our work. So an additional privilege mode defined in the RISC-V spec is called supervisor mode. So again, this is an optional part of the spec, and this is common. This is a mode that's not present in a lot of the common embedded designs, RISC-V designs that are out there now. So for example, the Sci-5 family, like the E31 and so on, these cores do not have a supervisor mode. However, the next mode, user mode or U mode, another one of the optional mode, this is common in the embedded RISC-V designs, such as the Sci-5 family and a few other RISC-V designs out there. And so this is the mode that we focus on for this talk, and this is where we add support for user mode threads. If you're familiar with the Linux port for RISC-V, Linux uses these modes a little bit differently. So Linux actually runs, the Linux kernel itself runs in supervisor mode on the RISC-V port. The Linux port runs in supervisor mode. What runs in machine mode is the supervisor binary interface. So there's a project called OpenSBI, which implements kind of some low-level features of RISC-V. That runs in machine mode, the Linux kernel runs in supervisor mode, and then threads userspace runs in user mode. But for Zephyr, the Zephyr kernel will run in machine mode, and the user mode threads that we implement will now run in user mode. So the way that switching to different privilege modes works, just like in Linux, is to trap. So there's a there's an RISC-V instruction called ecall, which is used, which all the system calls, and switching is implemented on top of. So that's, for example, how we trap from an unprivileged mode into a higher privileged mode, is using the ecall instruction. So we'll get into those details in a little bit as well. Okay, so for the MPU, for the memory protection unit in RISC-V, the RISC-V terminology for this is physical memory protection. So this is referred to as PMP in the RISC-V spec. So like most things RISC-V, this also is an optional part of the spec. I have a link here to the spec where this is defined. There's a second volume of the RISC-V spec that defines the privileged architecture where this is discussed. But this is an optional part, so of course it's required to do protected memory, but it may not be available on the RISC-V core you have. So that's the first thing to check, actually, if you want to see if this work is relevant to your RISC-V design. So the PMP, the goal of the PMP is to validate and check all the accesses from supervisor and user mode to make sure that they're actually allowed. So the actually accesses from M mode, from machine mode, the high privilege modes are actually configurable, so you can have it in RISC-V. You can actually validate accesses from M mode as well if you like. So at a high level, the PMP basically can grant accesses to supervisor and user mode, or it can be used to just revoke accesses from machine mode. So there's two different ways it can be used there. Because by default, machine mode has access to everything, but you could use the PMP to revoke access to certain areas from machine mode as well. There's a special bit called a modify privilege bit in the PMP settings, where this can be used to actually, when you switch from modes, you can actually set this bit if you want to check privileges from the previous mode. So this is useful for some implementations of fault handling and so on. I won't get into the details there, but it's a useful kind of implementation detail for the RISC-V OS port. The thing that I want to highlight here, and we'll hit on a few times during the talk, is basically this number of PMP entries. So the RISC-V spec defines the number of PMP slots, the number of PMP entries actually as 16, but it's actually implementation dependent. So each of the RISC-V cores that are out there can choose how many PMP slots. So more commonly in cores that we've worked with, that number of slots has actually been half that, has been 8. So for example, the Sci5E cores that we worked with in this project, they all have only 8 PMP slots. So as we'll see shortly, that becomes quite limiting for the features we want to implement, or the regions that we want to protect with the PMP. So each PMP entry in RISC-V is actually configured with 2 registers. So one's an 8-bit register that defines read, write, execute permissions, as well as a few bits that define the type of entry that it is. So there are a handful of different types that are available. One is the on-off, to disable the entry altogether. TOR is top of region. NA4 is for a naturally aligned 4-byte access, and NAPOT is naturally aligned power of 2 region. So we'll get into that in a little bit more detail, because a few of those are relevant to our implementation here. So that's the config register, and then there's a 32-bit address register that's used to define the address of the region. And depending on the type, that address is used in different ways. So that's a 32-bit address register on the cores that we're talking about for this project, but of course for RV64 designs, that would be a 64-bit address register. So for the general case, if you want to use, if you want to protect some arbitrary memory region that's contiguous, you actually have to use 2 PMP entries. So you use one entry for the start address, and then you use one entry for the end address. And so here we start to see already, if you only have a small number of PMP slots, we're limited to the number of memory regions that we can actually define for protection in the PMP. However, there is a special case. If the region you want to protect is a naturally aligned power of 2, then you use one entry for the starting address, and then in the address register there's a special way to set up a mask in the least significant bits to indicate the size of the power of 2 size. So in that case, if you define the regions that you want to protect in the right way and they are naturally aligned, you can limit the number of PMP entries that you would use. So that's a quick overview of the RISC-V hardware features that we are used. So with the Zephyr background and the RISC-V hardware background out of the way, we can get into the implementation details. Okay, so one of the first things we need to do to implement a user space in Zephyr for a new architecture is first to detect what privilege mode we're in. So the Zephyr API provides this function, arches user context, which just returns true if the CPU is running within user mode, and returns false otherwise. So unfortunately on RISC-V there's not a simple implementation of this because we can't check the current mode from any privilege level. So from machine mode we can always check the privilege level, or the register that keeps track of this is accessible in machine mode, but it's not in user mode. So first thing we need to do is figure out a way to be able to check whether we're running in user mode from user mode. So the obvious first try was to just use a system call for this. So you use ecall to trap into kernel mode and check what the previous mode was, and then return. And that we implement that first. It was the obvious way to do it. And what we noticed right away is this function, this arches user context, is actually used in quite a few places. And was just adding a tremendous amount of overhead, so there were system calls happening every time this was called, and so it just ended up slowing things down. So we looked for another way to do this, and the way we ended up with was just using a global variable, or a global region, where we set a flag, and this flag is user. And so that can be checked from both user mode and from kernel mode. And this is just a 4-byte region that we protect with the PMP. So the smallest region you can actually protect with the MPU is a 4-byte region. So we make this region read-only from user space, and it's read-write from kernel mode. So from user space we can just read this variable and find out what our current state is. And then it's once we enter and exit kernel mode, we update this flag. So this ends up to be significantly faster, obviously, than doing a system call every time we want to check this value. However, with our limited number of PMP entries, we have to use this. We already are using one of them just to implement this this little global variable. But that's the way it's designed for now. So we'll get into this for future topics, but this is a potential area of revisiting this implementation. So getting into, so now that we can detect the current privilege mode, we get into system calls. So before we started this work, before we added a privileged user mode support, their system call infrastructure was already implemented for Zephyr on RISC-V, because system calls are used even from kernel mode. And so as mentioned, they're built on top of this trap handler, this ecall. So the ecall, this trap handler can be used from kernel mode as well. And it's used for a few different things. It's used to trigger context switches, so even between kernel threads, can be initiated by the operating system, and so those are built on top of kernel mode system calls. So when that's the kernel mode system calls are also used to handle the IRQ offload. So that's Zephyr terminology for what in Linux would be called soft IRQs or work queues, kind of deferred work that's initiated by an interrupt handler. So those things were already present before we started our work. So this is the system call infrastructure was in place for the Zephyr port for RISC-V already. So now we'll talk about what we added, what was needed to add user mode support to the system call infrastructure for RISC-V. So the first thing is just how to initiate a system call from user space. So from user mode running on the thread stack, what is used is a system call wrapper. So Zephyr API defines the system call wrappers already, and so for each architecture you need to implement these arch-syscall invoke functions that trigger system calls with various numbers of arguments. So those functions are built on top of this ecall instruction, which then traps into kernel mode or machine mode, or specifically on RISC-V. So once we trap into the kernel mode, the first thing that happens is switching from the user stack to the kernel stack. And so we save the exception stack and various parts of SOC context. And then we update this flag. So this is user flag that I just talked about. So this is our special kind of protected area that we use to detect, to keep track of whether we're in user mode or kernel mode. So we update that. So now we update that false. So because we're running in kernel mode. And then we check if this ecall trap actually came from kernel mode or not. So as I just mentioned, there's some infrastructure already in place for kernel mode system calls. So we first check that, and then handle those cases. So like I mentioned, these are there for kernel mode syscalls. But there's also the way to switch from kernel mode back into user mode, like on thread start, for example. We switch from kernel mode to user mode. There's a function, a system call that does that. Also, system call returns from kernel mode back to user space go through here. So we first handle any kernel mode system calls, and then we get into actually user mode system calls. So the way that's implemented now is once we get this far, we go and find the system call arguments that came from user space. So those are going to be in the exception stack frame. So we load the arguments, we load the system call ID, and validate all those to make sure it's a valid system call. And there's some basic checking done on the arguments to make sure they're all valid arguments. And then we actually trigger the system call. So this do syscall is kind of the generic Zephyr interface that does all the system call, the actual work of the system call. When that's done, the system call return path does a nested ecall, and so we end up back in in this part here where the ecall actually comes from kernel mode. We handle the system call return. And then we set our user flag back to true right before we return to user space. So now our variable is updated, so next time we check what mode we're in, we're now back into user mode. Okay, so adding on top of that now, we have the basic system call infrastructure in place. Now we can discuss how threads are actually implemented. So for a user thread, there's a few pieces here. So we'll talk about kind of the memory regions involved in a thread. So the first one, or the first couple that are the obvious ones, are the program text section and the read-only data that come from the basic compilation of a user mode thread. In Zephyr, these are actually combined by the linker script, so they become one region, and so the permissions are read and execute. These should be separated so that you could have the text section be executable only, and the read-only data obviously should be read-only. But as mentioned, with the limited number of PMP regions that can be protected, the current implementation actually combines these together, and so they have read and execute permissions for this combined area. So that's the first region. The second region is the thread stack that's separated from the text and data. So the thread stack that's per thread includes the thread local storage, and also threads have their own additional thread data and BSS sections that are in this area. So that all gets put on the thread stack and with permissions set accordingly. So for each of these, so those two regions, those have to be each get their own PMP entry. And so by default, these are not necessarily aligned. So the text and data obviously can be arbitrary size, and the thread stack can be defined at compile time. So unless these are aligned power of 2, each of them needs 2 PMP entries. That's already 4 PMP entries used for those. Combined, now we add, in the global variable that we just talked about, this is user flag. That uses one more PMP entry. So just to implement kind of a basic infrastructure for threads for arbitrary sized regions, we're already using 5 PMP entries of the 8 total on cores like the E31. So as you can see, this is kind of we start to see the limitations of a limited number of PMP slots. And so far we're just talking about user threads. Now if we add on top of that the memory domains, those threads, remember threads can also ask for memory domains that can be shared between threads or shared with the kernel. And so the number of memory domains is also limited. The number of memory domains that we can protect is limited by the remaining number of PMP slots. So there's a Zephyr API function. The first thing we want to know is how many partitions, actually memory domain partitions, we can there are available. So that function just returns the max number of PMP slots available to the architecture, minus the number that would be used by user space. So that would be the 8 minus 5 in the current design. But if user space is using power of 2, we can actually bring that down. So, but we'll get in that in a second. So the next API function is how to add a memory domain. So again, memory domains can be requested at build time or compile time, but they can be of arbitrary size. So if we want arbitrary size memory domains, then we need to use 2 PMP entries for each memory domain partition. And of course we only need 1 if it's a naturally aligned power of 2, but since that is not enforced, we have to take care there. So in the case where we're not using the naturally aligned power of 2, we already are using 5 for user space, and 2 for the first memory partition. So that means we've used 7 of 8. So because we need 2 for each memory partition, there's no more room for any memory partitions either. So just with a basic configuration of user space enabled plus a single memory domain partition, we've already used up all of our PMP slots. Well, all but 1, but we have to use 2 at a time, so we're effectively out. One more function in the memory domain partition API is this arch buffer validate function. So what that's available, that can be called from threads to see if the thread actually has access to a memory domain partition, either access or write access. And then what that function actually does is just walks the PMP entries to check if the thread can access that or not. So we are, as I mentioned, we're heavily limited by the number of PMP slots. So one of the things that we did in our implementation is to kind of, if user space is enabled, we use kconfig basically to automatically enable this power of 2 by default. So that allows everything to be, all these regions we just discussed, to be by default aligned on a power of 2. Of course, you can configure this out if you like, but this is just the defaults that are in by default now. So once user space is aligned or is enabled, the power of 2 feature is enabled. The power of 2 alignment feature is enabled, so that we can maximize the number of available PMP entries. But the memory domain partitions are not necessarily a compile time, so you still have to take care when you define your memory domain partitions to make those align on a power of 2 as well, to if you want to use and protect several of those regions. So that's the basics on user mode threads with memory domain protection. Another feature is this hardware stack protection. So if we want to protect our stacks, in addition to our kind of basic regions, memory regions used by threads, we need to use a few more PMP entries. So in Zephyr, you can have an interrupt stack, you can have a kernel mode privilege stack, and a user stack. So all of these we can protect. We can optionally protect with PMP if we'd like. So, however, we don't necessarily need to conflict with the user mode, the PMP uses for user mode, because once we're in kernel mode, we can save off the PMP entries for user mode, switch in our PMP entries for the kernel mode stacks, so we can use them. We don't necessarily have to keep them in saved in the PMP all the time. So they can be swapped in and out, at least for the IRQ stack and the kernel privilege stack. So that's the way things are done today. However, in Zephyr, all of these features can be enabled and disabled independently. So as we already saw with kconfig, we can enable user space and power of 2 alignment and the hardware stack protection kind of independently. So the various combinations of all these, so care has to be taken in the implementation so that we support the various combinations of these features as well. And each entry, each of these options affects the number of PMP entries that are used and needed. So the number of stacks that are protected, the number of memory domains that are protected, all are affected by all these options. So just we had to take some care and some checking in the implementation so that we actually can support these various features independently. So as hinted at in a couple areas, so that kind of covers the main implementation overview of the implementation details. So some of the challenges that we ran into and some ideas for future work. Well, the first one's not really a challenge, it's more future work. So this work was focused on the 32-bit RISC-V designs. So some work is needed to make this work on RV64, and that's primarily about the low-level trap handling and so on to make sure this stuff is working for 64-bit. But another area of potential interest for 64-bit is a lot of the RV64 designs actually support an S mode. So like Linux uses S mode, we could explore using running Zephyr in S mode. And that might allow some interesting work around having, just like Linux, having SBI run in machine mode and Zephyr running in S mode. So that's something we did not explore, but that's something that's worth exploring if we're thinking about Zephyr support for a 64-bit RISC-V. The other thing is this is user flag. So I'm sure you may have already noticed that we're just using, we have to use a 4-bit global variable to check this is user feature. And of course doing that way is not SMP safe. So right now there's only a single bit used. But since these cores that we're using so far are only single core, we haven't had this issue. But obviously we need to make that is user implementation SMP safe. So one way of doing that that we're already exploring is, since the smallest PMP region is 4 bytes, there's several bits available in there. They can just have a bit per CPU, so that can be tracked independently. So that's one way of doing it, but there's definitely other work that's needed to make this various parts of this implementation SMP safe. So that would be relevant, especially for the RV64 support as well, because most of those are multi-core. Another idea that we have to explore is RISC-V has these machine trap delegation registers. And so that would allow us to separate the user and kernel exception handling. So right now, as you may have seen in my slide about the eCall handling, there's lots of stuff going on in that eCall trap handler because it has to detect kernel mode system calls, user mode system calls, nested eCalls from various places. And that's all in a single function, which is getting rather large in the current port. So one idea we had was actually to use these delegation, at least we can explore as using these delegation registers, and that might allow us to clean up the code a little bit and handle kernel exception and interrupt handling separate from user exception handling. It's just an idea so far. We haven't actually done that, but we think there could be some improvements, at least in maintainability, readability of this kind of low-level code. One more idea was for the QEMU support. So we did some work, and before we were designing this on the Sci5 cores, we were doing work, initial work on QEMU, and we found out that the PMP emulation actually is not fully functional in QEMU for RISC-V. So Alex actually wrote a handful of patches to QEMU to support this, but there's still a bit more work that's needed to make this to support the various PMP features. Including playing with the number of slots and a few other type of things that are enforced in hardware that are not actually enforced in QEMU. So there's a bit of RISC-V related QEMU work to there. So one other area for some future work. So that kind of wraps up the talk. In summary, before we started, there was already a functional RISC-V port for Zephyr. It supported only the kernel mode in Zephyr, and it supported cores that have just the machine mode. But now, after our work, the RISC-V support for Zephyr supports user mode threads. It supports memory domains with protection. And it also supports the hardware stack protection using the PMP. So thank you so much for listening, for watching. We appreciate your attention. If you have any questions, you can reach us here at these email addresses. Alex is the one who did all the core engineering, so he'd be the one for technical questions. I can maybe help as well, but feel free to reach out. We'd be happy to talk to you about, especially around some of these ideas for future work. And thank you very much. This talk was brought to you by my barking dog. I'm not sure if the dog barking and the crows behind me actually came through the recording, but it was a little bit distracting. But we'll just say it was part of the plan. And part of life as we work from home. Anyway, thank you for watching, and goodbye.